Hello, welcome to the Spirit of Artemis. I'm your host, Mark Lesmeister. As I record this on April 4th, the Artemis II mission is well underway. The Orion spacecraft, which they have named Integrity, is on its way to its lunar flyby. If you've been watching the coverage of this mission, you might have seen that there are some terms that they're not really explaining very well, or there are some questions you might have about how all this works. And so I thought I'd put together a couple of videos similar to the ones I made for the Apollo missions, explaining some of the details of the Artemis mission. This one will cover the initial launch and post-launch events. And then a later episode will cover some of the orbital maneuvering that the Orion has been doing. After that, we will see where the news takes us. So I hope you enjoy these videos, and here's one about the initial operations after launch. Here's a video of the Artemis II launch stack on the launch pad. The system consists of the Space Launch System rockets and the Orion spacecraft, which will be launched into orbit by the SLS. The orange column in the center is the core stage. It houses the fuel and oxidizer for the 4 RS-25 engines. These engines are the same engines that powered the space shuttle. I don't just mean that the engines have the same design. 3 of the RS-25 engines in Artemis II were previously flown on space shuttle missions. The other engine was assembled from spare shuttle-era components. The white rockets alongside the core stage are the solid rocket boosters. These are similar to the solid rocket boosters on the shuttle, but they are a little larger and significantly more powerful. Together, these engines can provide almost 40 million newtons of thrust. That's about 9 million pounds. So here we are, just about ready to launch. At T-minus 33 seconds, the SLS rocket takes over the launch sequence. At about T-minus 6 seconds, the RS-25 engines will start. And then at T is equal to 0, the SRBs will ignite. Once the SRBs are lit up, they can't be turned off, and we are launching.
7. RS-25 engines lit. 4, 3, 2, 1. Booster ignition. And liftoff. The crew of Artemis II now bound for the moon.
Almost immediately after clearing the launch tower, the SLS executes a roll pitch maneuver.
Good roll pitch.
Roger, roll pitch.
Houston, now controlling the flight of Integrity on the Artemis II mission around the moon.
People often wonder why rockets don't just go straight up if the goal is to get to space. There are many reasons why a rocket might roll and pitch shortly after launch, including aerodynamics and even safety. But remember, the goal isn't just to get to space, it's to get to space and stay there for a while. And that means getting into orbit. So sometimes a rocket will point in a direction other than straight up, so that it isn't fighting against gravity as much, and more of the thrust then goes into gaining speed. To understand why speed is so important for achieving orbit, we will look at an explanation suggested by Isaac Newton himself. Imagine firing a cannonball from a horizontal cannon. The cannonball moves forward at a constant speed in the horizontal direction, while in the vertical direction it falls to Earth. If we fire the cannonball with a faster speed, it will hit the ground a little bit farther from the cannon. If we mount the cannon on top of a high mountain, so that there are no obstacles in the way of the cannonball, and fire it at a really fast speed, the cannonball will go a little farther than it would on flat terrain. This is because the curvature of the Earth means the cannonball takes a little bit longer to hit the ground. If we fire our cannonball at a really fast speed, then as the cannonball falls toward the ground, the Earth curves away at the same rate. The cannonball never gets any closer to the Earth. This is what it means to be in a circular orbit. This speed is about 7.7 kilometers per second, or 17,000 miles per hour at sea level.
Mission Control Houston seeing good performance on the 4 main engines, Space Launch System core stage. Integrity, 3 miles in altitude. Traveling more than 1,200 miles per hour.
As with everything else in science and engineering, there is a trade-off between speed and altitude. The faster the rocket goes, the more pressure it experiences from the surrounding air pressing up against it. The higher in the atmosphere the rocket goes, the less dense the air is, and so the less pressure is exerted by the air. Rocket scientists calculate this dynamic pressure using the formula Q is equal to rho v squared, where the Greek letter rho refers to the density, v is the speed of the rocket, and Q is the dynamic pressure. At some point in the flight, the speed will be fast enough and the air still dense enough so that the dynamic pressure will be at its greatest. This is called max Q, and it is an important checkpoint in a rocket launch.
Mission elapsed time, passing 1 minute, approaching max Q.
On, Ponce de Leon. Stan, we have you loud and clear on Ponce de Leon.
Have you the same?
Communication signal transfer confirmed as Integrity and its crew go supersonic.
Once the solid rocket boosters are used up, they separate from the core stage. The rocket will throttle back a little bit before this happens, and then throttle up as soon as the SRBs separate.
1 minute 50 seconds of mission elapsed time, standing by for main engine throttle down to 85%, ahead of solid rocket booster separation, expected at the 2 minute 9 second mark. We see throttle down. Confirmed separation. Main engines throttling up, guidance converged.
Just as with the Apollo missions, there is a launch abort system on the SLS. This consists of a rocket motor in a tower mounted on the fairings covering the Orion spacecraft. In an emergency, this motor can pull the Orion spacecraft off of the rocket stack, after which the Orion would use its parachute to splash down safely. Above 300,000 feet, the launch abort system is no longer feasible. The air is also thin enough that the fairings covering the Orion and the European service module are no longer necessary. The fairings covering the service module are jettisoned first. Then a smaller jettison motor in the launch abort system pulls it away from the Orion.
2 minutes 45 seconds of mission elapsed time into the Artemis II mission. Thrusters on Integrity and upper stage confirmed in a ready state ahead of service module fairing separation. 3 minutes into the flight. Integrity 49 miles in altitude, 78 miles downrange, now passing 5,000 miles per hour. Standing by for launch abort system jettison.
Houston Integrity, good last jettison, great view.
Copy, jettison. Team Eco 8+02.
The MECO referred to in that last radio call refers to the core stage main engine cutoff. As I said, that will occur at about mission elapsed time 8 minutes and 2 seconds. Following this, the core stage will separate from the second stage, which is known as the Interim Cryogenic Propulsion Stage, or ICPS.
About 10 seconds remaining until the main engine cutoff of the Space Launch System core stage. Standing by for confirmation of MECO and core stage separation.
Integrity and nominal MECO, core stage separated.